Καλώς ήρθατε στην ενότητα του workshop. Έχουμε την πολύ μεγάλη χαρά να έχουμε κοντά μας τον κύριο Chris Murphy, ο οποίος είναι τεχνικός διευθυντής της Viavi για την Ευρώπη και ο οποίος θα μας αναλύσει και θα μας πει περισσότερα πράγματα για το κομμάτι των μετρήσεων και με ποιους τρόπους και με ποια μοντέλα μπορούμε να κάνουμε το 5G και το 6G να είναι πιο δυνατό και πιο γρήγορο. Κοντά μας είναι ο κύριος Πατσούρας από την Acta, η εταιρεία η οποία αντιπροσωπεύει τη Viavi στην Ελλάδα και θα μπορέσει να μας κάνει μια πρώτη παρουσίαση. Κύριε Πατσούρα, Γιάννη, ο λόγος σε εσένα.
Thank you, Mr. Laskoudis. Good afternoon, everybody. As Mr. Laskoudis said, we have the honor to have Chris Murphy with us, the regional CTO of Viavi. Viavi is a long-standing partner of Acta. We use their solutions and we collaborate with them mostly for commercial projects. And in the last few years, we have collaborated with them for the EU R&D projects where we measure the network performance that was discussed in the mainstream of the conference. Chris will explain to us what are the elements that need to be modeled and measured in order to have a successful and optimized measurement and performance verification of the 5G and consequently 6G network. If Chris is ready, I will pass the floor to him to go to the main part of the session.
Thank you, Yanis, and thank you, Christos. I'm honoured to be invited at this conference, and I'm very happy to share some thoughts on this interesting area with you today. I shall share some slides. Okay, so as Yanis said, I represent Viavi Solutions. We've been quite a number of years now, and I'm going to try and cover a number of areas now. The drivers and trends which are taking us towards 5G and then onwards to 6G in the future. And specifically why we need data to understand our next generation networks. And there are a number of examples given earlier in the workshop of the different projects. The meta cities was interesting, and there were some use cases in the 5G tours and the European projects. So data is fundamental to a lot of these. But it's not just about understanding our network in its operation now. It's also about how do we use the data to deliver the use cases that the network is expected to deliver. So I'll try and build on that and then bridge it to the concept of digital twin. Again, we heard about this in the meta cities, specifically digital twins of the city itself and the ecosystem that makes up a city. To be able to model that is a tremendous asset, allowing us to perform all sorts of optimizations of our cities. But a digital twin of the network itself, the communication network, which provides part of the fabric for that city, is also an important concept and opens up a lot of doors. So I'll try and cover these subject areas in this presentation today. So we're asking an awful lot of our networks, of our next generation networks. We've got many different types of use cases that our networks are expected to perform. And we need to deliver more variety of use cases across many verticals of industry, including some that we haven't even thought of yet. And from the word go, 5G has been conceived to do this, and 6G is continuing that journey. And Yanis described the various 5G tours use cases. There were quite a few in there, like smart parking and follow me cars with remote monitoring and guidance, and some AR and VR applications, as well as the emergency situation management, such as the airport evacuation. And key to this is that it's not just that there's a wide range of use cases and services that need to be delivered, but they have such different types of SLAs associated with them. What makes a good AR VR application is quite different from what makes a good emergency situation management, and what SLAs we need to make to meet in terms of the data rates, the reliability and the latency. These can all be quite different across the different types of applications. And sometimes as a service provider, you're going to have penalties associated with not meeting those SLAs, particularly in some of the high value, high reliability use cases. So let's look at what is happening in mobile communications in order to, in terms of the trends and also how the networks are responding to those trends. So one of the key things about 5G and then the transition to 6G is that the radio architectures are getting very diverse. You've not only got to open up new bands of the network in order to satisfy the requirements to deliver throughput for the enhanced mobile broadband applications, but there's also the need to support many more types of devices for the massive machine type communication. And then the more overlays that you've got, the more reliability you have, because there's more redundancy in connectivity, so that satisfies the high reliability use cases. And there's also a big push towards energy saving. It's important to be able to have networks which aren't consuming ever more amounts of energy. And when we look at things like massive MIMO, if we just build those without any thought into it, then there'll be a massive uptick in the demand for energy to provide the communication. So there's a lot of drivers here. We want to achieve the use cases, but we've also got to work within the constraints of physics and also respect the societal goals such as energy saving. There's also drivers such as the limited footprint at the edge. So we can't just install a big physical footprint or for a radio. In all cases, we've got to be able to deploy solutions where we can centralize or bring some of the functionality more towards the center, away from that low, that edge of the network where the availability of space is low. And there's also the virtualization and cloudification. So the more that we can run on the cloud, either it being at a big data center or a metropolitan data center, that can reduce costs. And there's a trend towards centralization of the. There's also the trend towards low latency and having local breakout. So as well as a trend towards centralization in order to reduce cost and deal with the limited footprint, there's also the drive to decentralize some things when it makes sense for the services. So sometimes we find functions which normally live in the core network at the center appearing towards the edge for local breakout, for example, where the latency demands require it. And so we've got a bit of a tension there between centralization and edgeification. And then there's the network intelligence is being abstracted out of the networks. So the idea being that we can democratize the intelligence that's required to run the network reliably, and we can have solutions which are suitable for different applications in different use cases in different environments, and make sure that the network is able to be built to respond to the demands on it in order to achieve the SLAs that's expected. And then we've got new deployment scenarios such as the private networks, factory networks, airports mentioned earlier, and we need a network which is flexible in what it's being asked to deliver, and also dynamic, so that it's able to respond to the stimuli on it in terms of the impairments and the external interferers and failures, as well as the changing demands from the customers. So key to this is the ability to measure the network, and Yannis, in his presentation about ACTA earlier, he described quite a few ways that we can measure the performance of the network, and that's key for sure. And there's many ways that we can measure the network. Here's a few examples of the ways we might want to monitor the network. But there's also the split between the edge and more towards the center, the transport infrastructure, the compute fabric, the the network functions and the core and the RAN. There's many ways we can think about this, as well as active test and passive test. So the more data we have and the more rich and granular the data is, the more visibility we have of the network, and the more we can understand how it's performing, and more importantly, when it's not performing the way we want it to. And we can envisage all sorts of use cases of having more data in terms of modeling the network, understanding how it might perform in different scenarios. But we can't just continue to generate and consume more and more data, because there's a cost here. There's the cost to collecting data and storing it, processing it and performing the analytics, the cost of the whatever compute and other monitoring solutions that we're going to deploy, and also the transport network. If we're collecting lots of data towards the edge and we have to transport it to an analytics solution, then there's an impact on the transport network. So there's a tension here. On the one hand, we want more data. On the other hand, we want less data. And there are various solutions to this, such as managing the data, making sure that we only collect what's needed, and that we manage the retirement of data when it's no longer valuable. We can, instead of collecting data about all of the activity, we can have bellwether sampling rather than full census collection. We can distribute our data collection and analytics to the edge or other parts of the network, so the data can be processed where it's collected, and then the essence of the data can be then transmitted to an analytics solution. But data is not the only. Data has many applications. If we collect the data as described in Yannis's presentation, we can really understand the performance, and we can understand when it's performing, when it's not performing, when there are impairments, and when we need to respond to those. But let's think about what are the outcomes that we actually want from our network, and how can data help us with these? Well, we want to optimize the interactions between the HetNet layers. So there were many layers on that early slide I showed, with the macro cells, the massive MIMO, the low band, mid band, millimeter wave, interworking with older technologies, 2G, 3G, 4G, and then there's the what will be coming with 6G, things like intelligent services and components of the network which will have embedded intelligence. So making these all work together is not a simple matter, but it's something which we have the goal with all this data that we want to collect in order to achieve. We need to, the service provider, it's not just about managing those interactions between the HetNet layers, but it's also about delivering the SLAs. And unless we can deliver the SLAs for the different services we're offering, then we failed in optimizing the interactions between the HetNet layers. We also want to deliver the performance that's necessary and required for the SLAs, but also to minimize the energy consumption. We also want to be able to train the intelligence. We have the intelligence abstracted out into the near real-time RIC and the non-real-time RIC as defined by the O-RAN Alliance. And these things will need data in order to train them, so they can understand the performance of the network and they can respond to stimuli on the network. And we may want to even validate and train our intelligence before we deploy to the network. So having solutions in the lab, so we can go with confidence to the live network with these novel solutions. This is going to be a key step in making 5G a reality. So the communication networks which are highly complex, and data can help us to understand the complexity. But I want to think now in terms of the stimuli on the network, which is the things which are affecting the network to change the way they operate, and that can be. Well, I think of these in a couple of categories. So stimuli are things that we can't control typically, or we can't directly control. And that can be like the utilization of the network. So how are the subscribers on the network using the network in terms of the services they want to use, their spatiotemporal characteristics, how are they moving around, when do they want the services, what radio resources are they using, but also the transport infrastructure that's required to deliver that, as well as the compute resource for those virtualized aspects of the network, including the network functions and also the application services, as well as the core network for that matter. And there's also impairments. These are stimuli. An impairment is a stimulus that we can't really control. But we can understand it, and we can think about failures in the algorithms, in the intelligence. There are failures in the hardware, a compute node falling over. The fiber network, which is conveying the transport, could be subject to a breakage or a more subtle strain, which is reducing its performance over time. The network functions can fail. There could be an external interferer which suddenly appears, or maybe transient and impairs the network in a way it's difficult to detect. There could be rogue UEs, either because they have bugs in them or because someone is acting maliciously. So there's many impairments that we can consider as stimuli on the network. So these are stimuli, things that we can't control. And I contrast these, the stimuli, with levers, which are things that we can control. And we can think about the levers on the network. We can choose where to place the virtual functions in order to most optimally use the compute resource we have available, as well as deliver the service level agreements and the latency requirements we have for different services. We can decide how we prioritize data and how do we route the connectivity throughout the transport network. These are things that we can control, and that the industry is moving towards in an automation sense, being able to do autonomously. And there's also the radio network itself has many parameters, from the physical parameters, so where are the cells placed, and then how are they configured in terms of their antenna orientations and tilts, beam configurations, as well as things like the neighbors that are configured and how handover decisions are made, and the thresholds associated with that. And then there's things like traffic steering and the routing and traffic areas that are configured, and then scheduling decisions. These are all aspects of the network, levers that we can to some degree control in order to respond to stimuli in the network. So we have a number of impacts on the network, the stimuli and the levers. So how do we know how to control the levers in response to the stimuli that we experience? So let's think about this for a moment. So we've got algorithms. So algorithms, we can conceive of writing algorithms which could be explicitly programmed pieces of software containing recipes. They could be policies encoded in the system around things like scheduling, for example, or handovers. Human expertise and insights can directly go in and control some of these parameters. And the algorithms can be centralized, or they can be distributed, depending on how we design the algorithms, and also the timescales of which decisions are needed to be made. But when we make changes in a network which is as complex as a communication system, any change in one layer is typically going to have cross-domain impacts. So if we change the way that traffic is distributed between cells because we've done a coverage and capacity optimization, that can have an impact on how the routing takes place in the network, and it might have secondary effects or tertiary effects on the transport network, on the core network, on the compute infrastructure. So just building algorithms isn't an answer in itself, because it's hard to consider the big picture if we provide point-wise solutions to the complexity problem. So another piece here is the data, and we talked about that, and as I say, there was a lot of examples of the different types of data that ACTA are dealing with, and Ioannis just covered the 5G tours and the 5G Heart projects. And so there's various ways we can think of data collection. We can measure physical entities such as the transport network. We can measure virtual entities such as the network functions. Entities can report their own data, or they can be measured using agents embedded in the network. And there's all sorts of ways that we can collect data and process it and analyze it subsequently. And models, I think, is a key underpinning for the bridging between data and algorithms. If we have models, then we can do more with our data. So we can use models to reduce the dimensionality of our data. So if we have a huge amount of data, we can reduce the dimensionality and keep the essence that is important for driving our use cases and our understanding of the network, but without quite so much need to store the data and process it. If there's missing data, we can perhaps impute it using models and supplements, make a more enriched data set. And we can even use models to predict the future. So predict what some of the data will be in the future so we can anticipate how to respond to it. And then in terms of supporting algorithms, we can think of models as the typical 4 categories that I often see as descriptive analytics, what's happening, diagnostic analytics, why is it happening, predictive analytics, what's going to happen, and prescriptive analytics, what should I do about it? And if we can do all of these, then we are in good shape. But as we get more and more mature models here, these allow us to build better, more performant algorithms. But we get closer and closer to a representation of the network response. As we build these more sophisticated models, we get close towards something which is looking like a digital twin. And we heard about digital twin earlier in the MetaCities project. Building a digital twin of a city is a great asset, but building a digital twin of a mobile network can also be a great asset for us. And we can think of digital twin in what would a digital twin of a mobile network look like? There's many ways that we can think of modeling the network in a way that we can ask questions of it and interrogate it as to what would happen, run what-if scenarios. Everything from the physical configuration and how it's parameterized through the demands on the network. You know, where are the demands and what are the UEs doing over time and space, and thinking about how the radio layer works from the channel and radio propagation through to the network function behavior, and then doing what-if scenarios on top of that. So we can think of our digital twin in many dimensions. And then if we have a digital twin, there's what can we do with it? Well, there's many applications in the field and also in the lab, I would say. And you might even have a CI/CD pipeline, in which case we have some applications there. So thinking about in the lab, if you have a digital twin of your network, you can validate the XNR apps. You can make sure that they're delivering the performance improvements that they're supposed to be doing. You can validate, compare the performance of different XNR apps against each other or against different versions of the same XApp. You can quantify the impact of the system performance improvements, and you can also think of the whole RIC system with its set of applications running on it. You can validate that as well using a digital twin. As you get to a CI/CD pipeline, then you can build in some checks and balances to make sure that before those apps updates or new apps go to the field, that they are performant and they pass some basic safety and security and performance checks. But you can also think about training an XApp. If an XApp is based on machine learning, then it will probably have some components of a ramp up where it needs to be able to learn about its environment. So this means that potentially you go to the field and you have an XApp which is new, hasn't been trained. Can this training be done as part of the CI/CD pipeline? And if it can, then you can put the XApp into the field, ready trained for that environment using a digital twin. And then in the field itself, we can think of applications. So the ongoing training of the XApp or RApp. So the network will change, the stimuli on the network, the way the subscribers are using it will change over time. There may be impairments, failures, things like that, which will change the performance. And so having an XApp that's able to respond to that by ongoing learning, then the digital twin can support it in the field. You can also get conflicts between XApps and RApps, such that one XApp may say to do one thing, another XApp may say to do something different, which is in conflict. And if we can arbitrate between those using a digital twin, as well as making a gatekeeper just to do a basic sanity check if an XApp wants to make a change to the CUs or the DUs, for example, we can validate that decision beforehand. So here we have a representation of a digital twin for a mobile network. And I would cast our minds back now to the start of this workshop when we talked about metacities, and there was a data being collected from the operations of the city to build a digital twin for that city. And can we even bring those digital twins together, the digital twin for the city with the digital twin for the mobile network, so that these things can be optimized in concert? I would pose that as a thought for the listeners. So that's my presentation. So I'm happy to take some questions, but just to summarize, data is key to understanding our networks, but it's not just about understanding the operation of the network now, it's also about building models to support better optimization of the networks, and then even to build digital twins, which allow us to do many more things than the simple optimizations that we can envisage initially. So thank you for your time and attention, and I hand it back to the chair.
Thanks a lot, Mr. Murphy. It's very interesting, all of this. I don't have any questions from someone, but if someone sends me any question, I will send you by email.
Thank you. Thank you, Christos.
Thank you.
Also from my side, Chris, this was very insightful what you presented, because it shows the transition path from collecting measurements through modeling to using this in a predictive way. And particularly, I was personally, well, to say impressed, but I did not, so far, have not made the connection between CI/CD, because this has also operational consequences. And this is something that is not very often brought to the surface. So this was very good. Thank you.
Thank you, Jan.
Σας ευχαριστούμε πάρα πολύ για την προσοχή σας. Σας περιμένουμε στα επόμενα συνεδριά μας. Thank you.
Thank you. Bye.
Thank you.